Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over Coulomb's law and how it applies to the atom. So let's get into this. So here we have Coulomb's law, and basically what you have here is you have energy is equal to some constant 1 over 4 pi, and then this is some constant that we don't really need to get into, but it's important that this is just a constant, whatever that number is. But the really important part of this equation is right here. So here you have two charges. Q is for some charge. So you have charge number 1 multiplied by charge number 2 divided by the distance between those two charges. Okay, so this equation really does explain a lot about what's going on in the atom with regard to electrons and shielding effect and stuff like that, and effective nuclear charge and things of that nature. And so we have to understand what's going on. And so in the atom, we have charges. So we have the nucleus. So I have three atoms here, and this is the nucleus with one proton. This one has two protons. This one has three protons. And so when we're thinking about this law here, basically what it's saying is that the energy in the system of these charged particles is going to depend on the charges of the charged particles and the distance between those charged particles. So there's a few things to note here. First, when we have like charges, the potential energy is going to be positive. And when we're thinking about potential energy in the atom, it's very much like potential energy, gravitational potential energy when we're thinking about gravitational fields, right? So I, standing on the ground right now, I have a low gravitational potential energy because I am close to the ground. I'm closer to the center of the earth as compared to like if I was flying in an airplane, right? So the farther I get away from the earth, the higher my gravitational potential energy. So as the distance between me and the earth increases, so does my potential energy. And so the default position, or the natural position for me to be in, is low potential energy. So if I jump out of the airplane, I'm going to be falling to the ground, lowering my potential energy, increasing my kinetic energy, and so on. So it's very similar to what we see in the atom. So when the particles are oppositely charged, they like to be close together. But if they are negatively charged, or I'm sorry, if they have the same charge, then they're not really going to be liking to be close together. So, what does that mean? How does this law like apply to that? So here, let's assume we have like charges. Okay, so if we have, I'm going to use a different color. So if we have two plus charges, two positive charges, it could be two negative charges too, but if we have two of the same charge, then we know that like charges repel. They don't really want to be close to each other. So let's imagine for a moment that we're trying to bring them closer together. So first, we notice that these two multiplied together, if I have a positive charge multiplied by a positive charge, then that's going to make the potential energy positive. The nature wants to have low potential energy, and that goes the same for anything in the atom. So the atom itself is trying to reach the lowest potential energy possible. And so when you have two like charges that are close to each other, um, if you lower the distance here, if r, being the distance between the charges, gets smaller, right? What happens to this whole thing, right? If r gets smaller, then this whole thing gets larger, and therefore the potential energy becomes more positive. So higher potential energy. That is not a good system. That's not a good position to be in. We don't want high potential energy. So you can understand that when we bring the two like charges closer together, that's raising the potential energy, right? That is not what the system wants. The system wants to go to low potential energy. So what are the charged particles going to want to do? They're going to want to repel and get away from each other, right? So getting away from each other lowers the potential energy. So if we make the distance between the like charges larger, then this gets larger, the denominator gets larger. That means this whole thing gets smaller and potential energy goes down. So like charges want to repel, they want to remove away from each other in order to lower the potential energy, because potential energy is positive and we want that less and less positive. Okay, same thing for negative charges. Okay, well, what about opposite charges, right? So if I have one of these, let me use a different color. Let's use blue. So what happens when I have a negative charge with a positive charge? So we're multiplying those charges together. If I have a negative multiplied by a positive, that's going to make the potential energy negative. So now the potential energy is negative. So now what happens with regard to distance? So if I decrease the distance between the two charges, if I make them come closer together, what happens now? Same thing happens, right? So this gets smaller. That means that this whole thing gets larger. But now instead of being a larger positive value, it's a larger negative value, which means more negative potential energy means lower potential energy. So they want to get closer together. That if opposites get closer together, that's going to lower the potential energy, and it's going to be more. They're going to be more happy, a more happy system, if you want to put it that way. All right. So this explains why opposites attract. They're attracting in order to lower the potential energy. So if we bring those charges apart, if we try to separate them and increase the distance, R here gets larger, right? So when R being a denominator, the distance between the charged particles gets larger, then this whole number here, this ratio gets smaller, and we end up with a smaller negative number. So in this case, it's becoming less negative. So another way you could put it is larger potential energy. Less negative potential energy is a larger potential energy. That is not a favorable system. That's not a favorable situation to be in. So separating those oppositely charged particles increases potential energy. So they want to be charged. They want to be attracted to each other. They want to become closer together, and that's going to lower potential energy. And again, we want to lower the potential energy, or the system or the atom is looking to lower potential energy. Okay, so with that out of the way, if we now fully understand the equation, we can now apply it to atoms with various amounts of electrons. So here we have a basic atom. This is your hydrogen, because we only have one proton. So we have a hydrogen atom in here with the one electron. So here, the electron and the proton, we have one, the nucleus is positive. So the nucleus is one charge, right? We can think of that as Q1, or in this case, we can say Q2 is the positive nucleus and Q1 is the negative electron. And so here we would expect an attractive force. So an attraction between those two. And so being as close as the electron can to the nucleus would be the lowest possible energy. So this explains the Aufbau principle in the electron configurations. Like electrons want to be in the lowest energy states possible. That means they want to be as close to the nucleus as possible. So lower energy states are closer to the nucleus than farther away. As you get farther away, the potential energy increases. So that why? Because the electrons and the protons, the nucleus is positive, So they want to be attracted to each other. They want to decrease that distance. So again, negative times positive gives you a negative uh, potential energy. Um, so electrons want to be close to the positive nucleus. So what happens when we put another electron into the orbit here? So here we have two protons, right? Um, so here we have helium with two protons. So the other thing we want to look at is now we have like charges here. So we have two electrons. They're in the same orbital. They're at the same energy level. And so what's these two electrons going to want to do? They're going to want to repel each other. And so having those two like charges in the same orbital, that's going to, if we keep them together, that's going to raise potential energy. So what are these electrons going to want to do? They're going to want to repel each other and move farther apart, right? So this repelling force between the two electrons is going to counteract to some degree the attractive force of the protons in the nucleus that are attracted to the electrons. So not only are the two electrons attracted to the positive nucleus, therefore that they're going to want to come closer to the nucleus in order to lower the potential energy, but the two like charges are going to want to repel in order to also lower that potential energy. So there's some give and take here. So the repelling force, it has to counteract in some degree the positive attractive force in the nucleus, and in that we call that shielding or um, the effective nuclear charge. So there's some shielding going on here with the repelling force here, and so these two electrons, because they are repelling each other, that's going to counteract some of the attractive force of the nucleus. And so these two electrons are not going to quite feel the exact strength or the total pulling force of the nucleus because of the repelling force of the electrons. So there is some shielding going on here. So these electrons are kind of shielding each other from the attractive force of the nucleus. And so here, I also want to point out the fact that we have two protons in this nucleus. So this nucleus has a total of a 2 plus charge. So not only does the signs of the charges matter, but the size of the charge itself. So larger charges are going to either have a stronger repelling force or a stronger attractive force if they're opposite. So if they're the same, they're going to have a stronger repelling force. If they're opposite charged, they're going to have a stronger attractive force. So here we have a larger nucleus. So that larger nucleus with more protons in it is going to have a stronger attractive force, and therefore the potential energy is going to be greater or less depending on the charges. So here we have two protons versus one. So if they're oppositely charged, then having a larger charge is going to affect and make a larger negative potential energy. Okay, so this is going to have a greater effect on the pulling of the electrons, and so we can see here also in this one. So this would be lithium with 3 protons. So we have lithium here. And so here you can see we have this energy level number 1, n equals 1, and now we're adding a second energy level, so energy level number 2. And now we have electrons in the energy level here. And so if we're looking at this electron here, this electron is farther from the nucleus. So it's not going to feel as much of a pull. So because these two electrons are occupying the lower energy, this electron has nowhere else to go except for just to go to the next higher one, which would be your 2s orbital. Okay, and so here, this electron is farther away, so it's going to have a higher potential energy, but it's as low as it can get. So higher potential energy because it's farther away, increasing R. Okay. But at the same time, you can see that these two electrons are on the inside. Both of these electrons are going to have a repelling force on this. So you can see this as a 2 negative. So our negative charge will be 2, right? And then we have a negative charge here, right? So we have 2 negative, 1 negative. So you can see that these charges in the middle here on the inside are going to have a stronger effect on this electron here on the outside. So that these two electrons have a repelling force on this one. Therefore, these two are counteracting the pulling force of the 3 protons in this nucleus on that electron. So there's some counteracting there. And so because of this, we call this shielding, right? These two electrons are shielding the positive effect of the 3 protons on this one. If these 2 electrons were taken away and only that electron was there, then the 3 protons would be able to have a full effect on that electron without any repulsion or repelling force due to these. But because you have these 2 electrons there, you've got those charges. So since they're like charges, those like charges do not want to be close together. They are repelling. To lower the potential energy, they want to be farther apart. But in order to be farther apart, you got to increase the distance. But at the same time, you have that attractive force in the nucleus. That attractive force is wanting to attract. So this electron also wants to be attracted to the proton, and being close together lowers potential energy. So there's that. Sorry about that. So there's that counteracting force. And so because of that counteracting force and all these different attractive and repelling forces, there's got to be an ultimate balance between these. And that's what we refer to shielding. So increasing the protons in the nucleus increases the attractive force between the 2 charges, the oppositely charged particles, in this case, the nucleus and the electron. Therefore, that's going to decrease the decrease the potential energy, make it more negative. So that's going to allow the electrons to become closer, be attracted more strongly. But again, adding electrons to it will also add a repulsive force. And so in order to lower potential energy, they're going to want to get farther apart. So understanding what's going on in the atom with regard to Coulomb's law helps us in the end to understand what's going on with the periodic trends. And so this is really the background and understanding of periodic trends as far as why does the effective nuclear charge change when you go in a certain way when you go across. Why does it across the periodic table left to right? Why does the ionization energy change the way it does? Why does the size of the atom change the way it does? It all comes back to Coulomb's law. So understanding what's going on here will actually explain everything with regard to periodic trends, which I will be talking about in future videos. Thanks for joining me. If you liked this video, if you learned a lot from this video, if this was informative, please smash that like button. Subscribe to my channel, hit that notification bell so you can be notified of other videos I put out, and put a comment in the comment section. Let me know what you think. Let me know if you have any questions I can answer. Thanks for joining me. Have a great day.